Right, okay, so I've got a very enviable job, which is to, first of all, summarize the talks that we've heard, and then afterwards to try and get you folks to start talking and discussing what, what's very important in terms of formation of planets, both in the inner disk, but also to some extent the outer disk as well. So I put this picture on. I was told, do not talk about your own work, all right? So I won't. However, I just want to remind people, everything is happening in there within 1 AU of the star, of this disk, but it is at the same time launching these wonderful jets which stretch for hundreds of thousands of AU, okay? So that's the bigger scale picture. Now I'll shut up about jets. Okay, so I'll attempt to summarize, so this, if you like, chapter of the meeting. I'm reminded of, there was a famous Irish writer, Nobel Prize winner, George Bernard Shaw, who sent a letter to a friend and apologized because it was too long. He said he didn't have the time to write a short letter. Okay, so it's a bit like that, trying to condense everything is, difficult. Now, we've all heard about, the facilities such as ALMA, more recently JWST, also the interferometers such as CHARA, gravity, etc., are making big inroads into our science and really probing the conditions in this inner disks. And alongside, of course, we have really dramatically improved MHD and non-ideal MHD simulations that are equally, raising questions as well as solving some problems. And we've a number of talks, or had a number of talks on this topics. And likewise, I think the other theme was that multi-epoch studies are also very, very important. And over 10, 20 years or so, the changes that will be observed are very important. Okay, so what should we alter about Lee's iconic cartoon, right? Well, there are a few things which I shall mention. I think Lee would be happy about some alterations at this stage. It's nearly 10 years, a whole decade, almost. Yeah, it's time for a change. Now, I was thinking about this problem. Oops. In our nice hotel, in this turbulent disk, and I decided to sit in there and think about what this all meant. And I definitely decided that the turbulent inner disk is the origin of water worlds. And maybe steamy worlds as well, but that's the only bit of inspiration I got from our hotel. Okay, so we had a number of talks. To start with about ZDI or ZDI if you're European, and the importance of magnetic fields. And Bonnie gave a rather nice presentation explaining how ZDI works. But what was clear from this is that the magnetic fields were seen in T-Tauri stars, and even now I think there's 1 or 2 class 1 objects as well, that their fields are complicated. They're not simple dipoles in many cases. You have octopoles, etc. And of course, they're also dynamo fields, and there's no remnants in case, a number of years back people were suggesting maybe there's some remnant of the field, the fossil field or whatever from the disk, but that's not true. They are definitely dynamo fields we're looking at. But she also emphasized how difficult it is to find new exoplanets in that environment. I mean, these are really, really interesting planets, very early stages, but from an observational perspective, it's very difficult to do. So we looked at, Michael Cecil looked at the inner disk, and there's also a rather nice poster as well I urge you to have a look at by Morgan Williams and Subbu Mohanty on this inner disk region and the instabilities that occur there. He showed how you can generate pressure bumps and pebble traps, and this could lead to planet formation in the terrestrial zone. So, there as well, there was a number of instabilities that were seen, and likewise, as I mentioned in Morgan Williams and Subbu's paper. The complexity of star disks with their dust sublimation zone was made also described very well by John Monnier, and also in a later presentation by Nuru. And they imaged in particular this Herbig AEB star, the C off-centered emission, which possibly indicating binarity. But what is very interesting now, and this is again into the area of the multi-epoch imaging and multi-epoch interferometry, we can actually see structures rotating. In this case, at sub-Keplerian velocity for that position, and therefore perhaps influenced by planets outside. Then the VLTI has been used again for looking at a number of disks, including this one, HD 14432. What we see now, of course, is that we can look at the different features that are present, that there's iron and magnesium silicates in there, and we can see orbiting clumps in systems such as DX-CHA. And so, you know, things are really moving on there. And I forgot about the action item on that one. Okay. So, Zhaoun Zhu described a really nice model for slow rotators and fast rotators and what happens, starting with a very slow rotator, perhaps a little bit unrealistic, and the star's not rotating at all. We know T-Tauri stars and Herbig AEB stars rotate. But what was seen is that when you get faster spin, it suppresses the well-known interchange instability. You get hotter spots on the surface and stronger outflows. And the equilibrium spin is when the truncation radius is about 0.78 of the co-rotation radius. And that looks always those numbers used to mystify me years ago, that these two numbers were so close. And it's like the anthropic principle or something. But anyway, would the world be very different if we had different numbers there? Okay, so you see hotspots, variability, that's consistent with those observations. Now, Stefan Krauss was looking very much into the future, I think, and the idea of looking at the circumbinary disks, and very much an important case for the VLTI and beyond the VLTI, in fact, and interferometers in general. And he was talking about the fact that, you know, in some cases now, and this is very important from the point of view, if we have enough sensitivity, 3D, to measure the 3D velocity field, as in the case of the Herbig AEB star, MWC 297. And there is an instrument which we're looking forward to its operation on Paranal, Asgard Bifrost, which will be able to look at quite a large number of lines, and some of these are very important from the point of view of accretion tracers and also outflow tracers as well, Don't forget that some of these lines that we're using as accretion tracers are also outflow tracers, and you have to try and disentangle the two, and that can get very difficult at times, and including, which will be very interesting, the helium-1 line. So that's coming on probably on stream next year. Sierra Grant gave you a kind of snapshot of what we're finding in the case of the mid-infrared instrument on JWST and the amazing spectra. And it really is, folks, early days yet. We're still trying to digest a lot of what MIRI has produced. But the big difference, and just I think it was Sierra's take-home message, was the difference between the very low mass stars and also the solar mass stars is in one case, you see in the case of the very low mass stars, a lot of hydrocarbons, whereas when you look at the solar-like type stars, lots and lots of water lines. And so that's clearly from the point of view of the evolution of the system, that's important to try and understand. And I know people in the room here have different opinions on the origin of this, so I think that's one of the things that will be important from a discussion point of view. Using again MIRI, this is looking at, and this was a bit of a surprise to me because our standard idea is the disks last 10 million years or so, and that's it. But it has been shown now with MIRI, with a medium resolution spectrograph, the MRS, that the H2 gas is present even up to something like 50 million years old in some systems. So that is interesting and might have some repercussions, at least in that type of system for planet migration, because the gas is still there and orbit circularization. There's also evidence of enhanced carbon in these old inner disks. Where I put the pointer. Oh, no, that's all right. No, yeah, but that's red, and this one's green because I'm Irish, okay? You thought I was joking, right? Anyway, you can see in the systems that are up to 30, 40 million years old, the C over O ratio is considerably enhanced, and so that's a very nice thing to find. I think also, incidentally, I mean, this idea of perhaps there's not as much in this meeting as maybe there should be on disk evolution over longer time scales. And if you have a look at Eric's poster as well, I mean, that's it's a shift in the paradigm as regards the evolution of these disks. So Agnes looked at this very interesting system, DQ tau. And what's interesting about it is that it's an eccentric binary, and it is a relatively short period, so it is possible with something like JWST to get time, a reasonable amount of time, and do something like 3 periastrons of this system. But during the periastron, then you get dumping, if you like, accretion going on. And this was very evident in the changes that were seen in MIRI over these different phases. And the changes were mostly in the inner disk, but you know, my impression was that the outer disk, it might be something else, such as shadowing and so forth. I should say at this point, a lot of people sent me slides and really and essential points, and that was really, really helpful in putting this summary together. Variations we're now seeing, and you know, 10 years ago, if you talked about variations in mid-infrared emission, you thought, well, maybe you'd have to wait a long, long time, but in effect, we're seeing this. I mean, obviously, there are variations from MIRI, the mid-infrared instrument on JWST. Once we got it properly calibrated, right, you could be sure then that we have differences from the Spitzer fluxes. And it was a surprise to many of us that these variations were clearly present in the mid-infrared. There's no doubt changes due to the star itself, but also it does look like there's changes in the disk structure and shadowing, which also there was a talk by Shangjie Zhang on this, and shadowing clearly, as you saw in the last talk, is very, very important. Okay. So, Takahiro Ueda spoke about what is called the dead zone, inner edge, and how that can shift, and therefore the formation of terrestrial-like planets may occur in a number of locations, and that it's not a frozen system by any means. But you really need more observations of this inner region and the conditions there to determine whether this is a possibility. I rather liked Carlos's talk on the extended disks, whereas the compact disks, you are so transparent, right? Yeah, so that kind of sums it up. Unfortunately, we know much less about the compact disks, but these are very, very common. And it is clear, however, they're very dense systems, and they can still form small planets, for example. And so the local environment may also be very important in these systems in some way. And I urge you to have a look at the poster then by Baron Portillo Ravello and et al., where, and is again something that's has not been mentioned very much at this meeting, is the influence of the nearby stars, particularly OB stars, on the disks themselves. Okay, Marbelle gave a very nice talk on the trapping of refractory species, so there's evidence that pebbles are actually trapped in the system, and as a result of that, you get less silicates, etc., in the inner region, and showed some very nice spectra that clearly indicate this is happening, for example, in the calcium lines and magnesium lines. So, okay, all right, so that is my kind of 20-minute summary of what's gone before, all right? And just is basically an aid memoir. I am not talking about my work, but I have a word from my sponsor, which is the Dublin Institute for Advanced Studies, which is, if anybody's interested, I'll use this occasion to advertise that we do have a professorship in astrophysics working on exoplanets. It has been advertised, and the preference is for somebody working on the early stages of exoplanet formation. So, if you look at the AAS job register, you'll see this position advertised, and the deadline is the end of the month. All right, so, okay, thank you. That's the summary. And it's time for discussion. I rather like this cartoon. We'll continue where we left off for the last meeting. The topic, I believe, was group discussions are a waste of time. Now, I don't believe that's true, all right? So, thanks. All right. Right. Now, I have, from a number of people I asked who talked, they sent in sort of a number of questions. We have one or two plants who I hope will will come up with some good questions, but let me just start the ball rolling with a question that was raised by Michael, Michael Cecil, and he was wondering about the stability issue of disks, right? So the analysis of the long-term stability of these regions, how well do we know how long these regions are stable for? And is that an issue? I mean, obviously, to some degree, we have to try and simplify the problem, but is this an issue, right? And also, just continuing on that theme, what are people's ideas on the really relevant physical processes that influence, and we've had a number of posters on this and papers on instabilities in the inner disk, and what are the important observations to do, multi-epoch observations to do, that will help us get a handle on this problem. Thoughts? Nope. Yep. Lee. Oh. Okay. Over here.
Thank you, Lee. Yeah, relevant physical processes. So one question I would have about the models is the role that the residual alpha in the dead zone is playing in driving the instabilities. What is the physical origin of that alpha? Can we think of plausible ways of generating an alpha in the dead zone in this particular part of the disk? And can we think of ways of quantifying it? That's probably from a theoretical standpoint, but I'd be interested to think about that because it may be playing an important role in driving the instabilities.
Okay, I mean, we've heard again and again in the sort of the dead zone region that there's an alpha, might be, depending upon who you talk to, 10 to the minus 4, 10 to the minus 5, whatever. What's determining that? Is that basically? Yep.
So on the observational side, and Adolfo and others can maybe say more about this, but one of the things that strikes me is that with Rubin, we'll see lots more outbursts, even though it's in the optical. One of the sad things is that NEOWISE is off, and it's really important to get, if there's some way that we can get some kind of comparable monitoring, or at least some monitoring in the infrared to complement the optical, because that tells you about where more clearly where the outbursts in the disks come from. I don't know what the possibilities are there.
So you're kind of worried that it's going to bias it towards, shall we say, more evolved sources, is that it? Because there will be monitoring, but it will be, yeah.
Well, it's not only that, but if you have a longer baseline wavelength, you can tell better where it's happening, what radius it's happening.
Yeah, I think I'll just add a comment to Lee's comment. One of the things that has come up in this meeting and then in previous meetings I've been at is the limited nature of the even ground-based near-infrared photometric follow-up. It is actually atrocious, the current state of the observational resources that we have compared to the optical, which will only get better than with Rubin. And so just getting K-band at high cadence, relatively high cadence in a determined manner. And we've heard all this wonderful VLTI work that is being trotted out here. And this is shown with, out in the photometric context where we don't really understand exactly what the disk is doing from a spectral energy distribution point of view. We just see this little snapshot the reconstruction of the inner disk from these baselines, and then we have to associate that with some other disk at some other time, or the same disk at some other time, and we have nothing to connect them at the same wavelengths. And so, a number of us who are interested in this would like to see this resource, which would involve rather modest aperture photometry, being deployed in some sort of robotic fashion, presumably from the southern hemisphere, because that's where most of the targets are, but northern would be good too. So, I see you. Wants to grab that? Take it somewhere else.
Yeah, in terms of monitoring, there's for sure the VVV and VVVX, which has done great work, but we definitely need more. I know that people should keep an eye on like what a lot of the our high energy colleagues are doing, because like there's the winter survey, which is turning on pretty soon, as well as Palomar-Gattini, which has been surveying the night sky, the northern night sky in J-band for the last couple of years. So there are some time domain experiments that are mostly being led right now by the high energy community. So I think we should probably jump on board and support those as well, because they're doing a lot of great work there.
Okay. Okay, well, I mean, I've got plenty of questions here, but, you know, if you, yeah, right.
And also, you know, the mics I think are active, so when I fall down.
Thanks.
Whoa.
You're tall, so
Giving Eric a lot of exercise here, you know.
So I just wanted to give a quick comment on the question that came before with the alpha in the dead zone and how important it is. So I would say that's a very good concern to have, and that's pretty much a caveat that most of the models have that investigate such instabilities. There are other models that do this as well. There was a paper earlier this year by DIAS and Vorobyov, I think, who showed such types of instabilities and that they inhibit the formation of streaming instability, for example, for long periods of time, making the planet formation much more difficult. But there might be a possibility, for example, where you have basically no alpha in the dead zone, basically zero, so you don't have to assume any hydrodynamic instabilities that lead to an alpha. But you have the surface layer accretion with the MRI active region and the transition still to the fully MRI active inner disk. And there are some models, I think, by Satoshi Okusumi from Japan that seem to indicate that this MRI activity can sort of reach into the dead zone a little bit to create some sort of alpha equivalent, so to speak, and giving a little spark in the dead zone. And this can actually be enough to like ignite the MRI in a very small region, which immediately leads to runaway heating and such instabilities. So there might be a possibility that we don't even need an alpha in the dead zone and still get instability cycles such as this one.
Okay. Can I ask a question about something I really didn't hear much about here, about in the case of the inner disk, we have the inner disk, of course, modeled by being irradiated by X-rays, etc. What about the low energy cosmic rays, or, you know, from the star itself, how they might affect the ionization? You know, because when you think about it, the T-Tauri stars, we've heard this, for example, from Bonnie Zayer's talk, that we're talking about fields on the surface, admittedly, of maybe a few thousand kilogauss. And therefore, the associated sphere is quite large and will exclude, certainly, some low-energy galactic cosmic rays. But we have cosmic rays from the star itself, if you like, the MEV or a few MEV, etc. should they be taken into consideration? Are they an important factor in ionizing at least the surface of these disks? Maybe.
I mean, from the meteorite record, we know there are short-lived radionuclides in the early solar system, that particular ones that were probably produced by solar energetic particles. So they were reaching material in the disk, and there are estimates of yields based on estimates of fluxes.
Mm-hmm.
So it happened here. And so I don't know if anybody has linked that to ionization rates, but maybe Steve has, so he's going to respond to that.
Yeah, Steve Dash, Arizona State. The radionuclides that are produced by the solar energetic particles, it's really only one that was produced significantly, chlorine-36, and it was produced very late in the disk, and it was probably a debris disk at that point. It looks pretty certain to me, and we reviewed this in the PP7 article, that all of the other radionuclides were just inherited from the molecular cloud. You don't see a big production of them. So there's certainly, a high X-ray flux, a lot of flares, a lot of particles, but we just don't see it really very much in the record.
Yeah, but could they still influence the inner disk, even if you don't see them in the nucleotide?
Personally, I don't see a big role for the MRI outside of the place where the temperature drops below 1,000 Kelvin. I think thermal ionization happens, but the role in ionization, making layered accretion, these sorts of things, I think it's subordinate to disk winds and other processes.
Okay.
I thought I would make 3 minor points. One is about the stability that you alluded to. And when we build up planets, their building blocks need to cross each other's orbit. So we started with chaos, but then we went into a state of order because, as we know it, solar system became very orderly. And the orbit crossing time now is lengthened to 10 to the 12 to 16 years. Mm-hmm. But then, as Poincaré pointed out, that all systems will eventually become unstable because of nonlinear effect. It just happened that we have not reached that in the solar system, mm-hmm. But if all 4 planets were to Jupiter mass at their present location, the orbit crossing time would be 5 million years. So, so there is some influence at birth that determines how long you can sustain order and before it transition to chaos. Yeah. Now, the fact that we see many of these multiple systems and there are multiple transit systems, they are so coplanar. And is that really consistent with what we think are these systems with lots of warps and very structured inner region? And I think that is an important issue, especially not just at the time of formation, but at the time when the disk goes away. And there's a long way from the time of emergence to the time of survival. So that's point number 1. Number 2, I think we also talked a lot about magnetic fields. We talked about magnetosphere. Let me remind you that this magnetosphere radius is determined under the assumption of ideal MHD. And Xiaohuan has shown very clearly that the role of reconnection. However, if you were to extend this, extrapolate this naturally to longer periods when the disk goes away, the so-called magnetosphere radius expands to very large distance because there's an m dot square on the bottom of that. So if they can achieve co-rotation, then T20 star should emerge as a very slow rotator. But we know that the peak may be at 8 days, maybe a little bit shorter or larger. But it's clear that the coupling between the field and the disk eventually vanishes. And what makes them vanish is possibility that we went away from ideal MHD. So when the magnetic diffusivity becomes large, then the coupling between the magnetosphere and the disk diminish. So when you look at your magnetosphere physics, and one should keep that in mind. Number 3, when we look at exoplanet surveys, people often claim there is a strong correlation between the stellar metallicity and the occurrence rate of gas giants, cold giants or hot giants. From the poster by Paula, you can see that the dust to gas ratio has a large spread, much larger than the correlation between the occurrence rate of gas giants and stellar metallicity. One should keep in mind all of the metal heavy elements inside the star went through the disk at some point. Some of it may have been early, some of it may have been later. But this dispersion that you see tells you that the metallicity of the disk is not necessarily the metallicity of the star. So therefore, the correlation that one finds just by simply dialing up the availability of building block material is probably oversimple-minded. That's just a few cautionary remarks. Thank you.
Thank you. Want to respond to that? Okay. So I'll ask about, this was some questions Takahiro Ueda proposed. And really it's about the innermost regions of the disks and how they relate to the outer disk, because we heard probably less about the outer disk, understandably, at this conference. But, you know, it's a horse and cart situation here, you know, you have to have both. And so in particular, the efficiency at which pebble delivery comes from the outer to the inner regions, okay? We need to cover dust in the outer disk as well, he's proposing, and then connecting the existing VLTI observations of the innermost parts of the disk regions with theoretical models is obviously important. But have people thoughts on this issue of the pebble transport? I mean, we seem to have a clear division here, of course, between the inner disk and the outer disk. That's fine. But about the pebble transport in this situation, what may be the dominant mechanisms or not, as the case may be?
I have a question about the first question. From Xiaowan's talk, if I understood correctly, the inner disk was heated quite a bit more than we expect from typical inner disk models. Did I understand correctly? So it was very much higher scale.
The higher scale height is due to magnetic support. So the temperature could still be low, but this thickness could be typically magnetic support. Yeah. So follow-up question. So then when people work on
planet migration in disks using the very thin disks, does that pressure support impact, your ability to open gaps and migrate?
So the disk, the gaps, it's harder to open if it's fully IDMHD because alpha is actually very high. It's much higher than people normally assume. Right? We assume 10 to negative 2 in the inner disks. But in the movie, you could see it's highly dynamic. Alpha is close to 1. So even Jupiter could not open a gap in these regions. Yeah, that's a good question. That's related with Doc's question. And the more we try to calculate the temperature self-consistently, the more we realize that this dust, the dust sublimation radii is actually very close to the magnetospheric truncation radii for T-Tauri stars. So for T-Tauri stars, the movie we see, we have an extended region of IDMHD. That may not be the case. It may be that we only have a small region which we reach to IDMHD, but then we start with dead zone. Only if we go to higher mass stars, like Herbig AEB stars, we could have an extended region for like IDMHD. But in most T-Tauri stars, that the dead zone inner edge will be very important in the magnetospheric equation. And so far, we don't have that treated self-consistently. So to treat that, we need to combine this magnetospheric equation simulation with Michael and Mario's radiation thermal simulation together to put everything together to get a self-consistent temperature and equation structure. So far, we have not reached there yet, but that can be done. These have been carried out separately, but we should be able to put them together so have a self-consistent temperature, ionization, MHD together.
And in your simulations, does the enhanced pressure, magnetic pressure support extend all the way through the ideal MHD region, all the way out to the dust sublimation radius?
Yes. In the IDMPD simulation, even without magnetospheric equation, just pure net vertical field simulation, people do see that the very thick magnetized surface layer. So I would expect in IDMHD that region will extend all the way to dead zone inner boundary. But beyond that, then the disk will be non-IDMHD dominated, and only the surface is IDMHD dominated. A lot of simulations we see from 10-tree simulation, now they do not have a very thick, highly puff up magnetized surface.
John first, yeah.
Oh, well, Ralph, if you wanted to follow up on this, go ahead. I had a different topic.
I was going to change topics, so.
Okay, so you're both going to change topics. So
Yeah, I just wanted to highlight that, a lot of what we know about, exoplanets are been focusing on T-Tauris and M-dwarfs, and, but what we know in terms of disks and trying to link, the pre-main sequence disk to the exoplanets that we see, we know a lot. The better we know more about the transition between T-Tauris and Herbigs than we do about T-Tauris and M-dwarfs, and going forward with the interferometry data as well as with ELTs and our ability to directly detect giant planets, and these disks will mostly be on the Herbig side, and so we like in the opening talks, we didn't hear much about the Herbig exoplanet or the intermediate mass exoplanet demographics. So just pointing out that it'd be good to see how we can, link these worlds up better and try to get more efforts into the exoplanets on the higher mass stars, which I know have troubles, but would be particularly productive in terms of linking to disks.
We will hear just on that later.
So, Ralph?
Well, I'd like to jump to Takehiro's second question on pebble delivery. There's a lot of interesting points tied up on being able to stop pebble flux in the interior. There's a pebble isolation mass that we all learned about that should shut things off when you get to be 20, 30 Earth masses or so. The recent simulations, 3D simulations, by I believe it's Huang et al. In 220, just this year, have shown that pretty conclusively that this is a leaky barrier. And I think Eve Lee and Martha Bryan have argued the importance of this for planet formation theory. Maybe she'll talk about that tomorrow. So these are not shutting off the flow to the interiors. If you thought so, then a Jupiter would cut off the flow and you could get very tiny planets in the interiors, and there's a lot of debate. I think we'll hear more about that later in the week. So pebble fluxes do make it through. And what that means for planet formation and disk chemistry is very important. So I think the one additional issue I'd like to add is these calculations are done when you have a planet that's creating the pressure bump. But suppose it's an MHD-produced structure. How leaky is an MHD-produced ring? Because those may be the most common things, because we're not finding the planets we should associated with all these rings. So that would be my provocative question, something I'm interested in calculating in my own group, but I think it's very much, we've seen that raised in a number of different talks here about MHD effects and how leaky they may be, with the point I would like to raise here.
Hi, Steve Desch again. Yeah, so we have the example of our solar system, and one of the revolutions in meteoritics that started about 2011 was the ability to identify where materials are coming from, the inner disk or the outer disk, probably separated by Jupiter. The whole suite of isotopic anomalies that just keeps getting reinforced. It's either NC or it's CC-like. And we are pretty sure that micron-sized dust crossed that gap, and to some extent chondrules that are about 100 microns did, but not mostly, and larger things simply could not. So Jupiter very effectively cut off the flux of anything, millimeter size, very effectively. And I think, personally, that the problem is not, that's fine. Let it shut off the pebble flux to the inner disk. I think there's a lot of evidence that you formed planets using pebbles, and I think that we're overestimating their ability to be lost through the inner edge and worrying about it and trying to bring them in from the outer disk when we shouldn't. They didn't come from the outer disk. They just didn't go anywhere. They just stayed there until planets used them up. That's what I think.
Okay. You know.
So I want to go backwards then, because we had Takahiro saying that empirically the fragmentation velocity is low. So you get left with a pileup of 100 micron size grains, very little pebbles. There's a poster out there by Yen-Sung Klein basically saying something similar, that the bouncing barrier basically allows things to stay small. And then you have Carlos's talk where, again, empirically, observationally, we see, emission at centimeter wavelengths, implying that there's pebbles there. So what's the disconnect? Where are we wrong in the physics here, or not? Or are there different systems doing different things somehow?
I don't have an answer to that. It was my question for the bouncing poster. I don't know how to put this together, actually. But I had a follow-up point also on this, and we have discussed about compact disks and how few we know about them. I want to highlight a paper by Osmar Guerra Alvarado in Lupus, where they have a resolution of 0.02 arc seconds in 73 disks, concluded that from that sample, 60% of the disks are compact, and the resolution that they reach at the visibility is like 0.6 AU, and most of those compact disks are substructureless. So we are seeing that these compact disks are truly, maybe some of them, the majority of them, substructureless, because this was a question from Lee on Monday, if I remember, of this, like, how do we know actually that these don't have pressure bumps? And I think we are starting to see that. And what I see is that these pressure bumps that will affect the delivery of pebbles need to be outside the snow line, right? So there is a point where the pressure bump becomes inefficient. It doesn't matter how close it is. So we do reach now that point close to the snow line to see that those, even if they have even closer structures, they are inefficient. So I think they may be a consensus there, yes.
Okay. So even in the more compact systems.
I have a question about the substructuralist comment, though, is because I was asking Carlos about this earlier, but isn't there a chance that a significant fraction of those substructuralist ones are just optically thick in the ALMA band still, as he was indicating with TG tau, and we would need like either very deep observations with VLA or NG-VLA to really get a good sampling of what the substructure actually is in these more compact disks?
Yes, this is a good point. And actually, in that paper of lupus, they also do relative transfer modeling and they conclude that most of these compact disks are optically thick. So yes, we would need to check that longer wavelengths. Yeah.
Yeah. Can I ask then a very general question to do with ALMA observations of these systems? Because ALMA has been trying to encourage people to. And it's difficult because of weather and so forth. Band 9, band 10 observations. Can those really help you? I mean, assuming the weather conditions are reasonable, will that help in the study of these compact disks or? Okay. All right. Okay.
If I can ask a question, because I know the experts are here, but what about things like Matisse? Can we hope to actually get some constraint on these with improvements in sensitivity? Because we may be talking about substructures that are very important at sort of AU to a few AU scales, right? So we just want to see if they're there. We don't actually have to.
Yeah, so we need N-band for that from Matisse because the shorter wavelengths probe rather the inner rim. So Gravity, Pioneer, and Matisse L-band is not that good. N-band is better. The sensitivity is not that great, but we have still nice sample. Just this data is really hard to analyze, so it takes time. Yeah. But I think that these few AU substructures should be pretty common in Herbig disks. In T-Tauris, it's less clear.
Okay, so is this a comment on that?
No, it's a comment on a previous. So I think the idea of trying to keep the velocity low, the fragmentation velocity low, to keep dust small, has implicit assumption that the dust you observe are primordial, but it's not guaranteed. There could be a multiple generation dust. Say if you have actually higher fragmentation velocity threshold, then you can form things efficiently, and then they may be too efficient, so they collide back to dust. And that's probably what we are seeing. So just another option to explain why there are so many dust. But this is very hard to model, as I understand it. So I think it has not been considered in many models. And also for a comment on a long time ago comment, one thing I think for dust to grow and to clumping and an effect has been often overlooked is the turbulence can diffuse dust. However, if you can have some mechanism that enhance dust density, the dust can reduce the diffusion from the gas, and that has been seen in simulations of dust gas interaction, but it's not easy to prescribe in a lot of global disk models. And I think that's an important part that could help dust grow to larger objects.
I have a fairly basic question as someone from the exoplanet community. So my understanding is that most of these extended disks are around fairly massive stars, A-type stars, sort of 2 solar mass stars, not necessarily?
No.
All right, okay. The compact disks, are they generally around solar mass stars? And following that up, assuming that compact disks are actually the ones that form the exoplanets that we end up seeing, how many stars with compact disks are there that are observable in a realistic sense from Earth using ALMA, James Webb, et cetera? Like what could our possible sample of compact disks be that we study? How many? Are we talking about 10 sources, 100, 1,000?
Carlos, I'm sure you have you have a comment, okay.
That is pointed to me. So apparently there's a stellar mass dependence that the size will be bigger for larger massive disks, stars, but we're talking about compact disks in context of similar type of stars. So for example, sun-like star, you can have larger ring disks. You can also have compact small disks, which are, I think we see them featureless in the past, but I do believe we see more evidence that those compact ones also have substructures, but in different kind of forms, locations. Yeah, but if we want to really study them very well, I think we are really reaching the limit of ALMA because we're already pushing to the 1 to 2 AU resolution. We do see something there, but it's really hard to get every disk down in that sense. For example, if we want to get one disk down very well, we need already a few hours integration on one target. Yeah. Can we study? That's limited by how much time ALMA will give us. Yeah. Yeah.
Like as you get farther away,
yeah, but we are focused on nearby young Stafford region, which is around 140 parsec-ish torus lupus. So you can study, I guess, tens of them at least. Yeah, tens. I think that hundreds are really hard. There are hundreds, but can we really study them, hundreds, very well in the next few years? I doubt that because we are losing long baseline in very shortly with ALMA. Yeah, yeah, right. How well do we, if we want to find there something, might be.
3 years is nothing. 3 years is nothing, but we have time on our side. Hey, I got 30 years for it. 3 years is nothing. If we think big, really, how many of these compact disks could our community study in the upcoming decade, 2 decades?
Yeah, I think we can do hundreds. If NGO welcomes, we can improve even for the very inner ones. Yeah. Now we only do 1 to 2 AU, that's the most we can do. In the future, we can do sub-AU resolution. Yeah.
Well, I think that there is a problem. I mean, you can observe them with ALMA, but if they are optically thick, you are not going to see anything. So the problem is that there are no any instrument working at long wavelength that we can actually see the optically thin emission from compact disks. So you have to support NGVLA for that.
Yeah, I think I mentioned too, band 6, 1 to 1 millimeter, so they are not that optically thick. So not that. So we are not pushing to band 9, band 10 because they are very optically thick. That's hard.
I think you can look at, maybe it's a good idea to look at band 9 because we can, it's optically thick, but we can get higher angular resolution. We can go to 10 milliarsecond resolution, and we can see if there are transition disks, in something with bit cavities in the small.
For those who are not all what's band 9? What do you want?
Band 9 is 0.45 millimeters.
But the issue with band 9 and 10 is weather, and On the other hand, that's why ALMA is at 15,000 feet and not 10,000 feet. So
That's true.
You know, the feeling with ALMA is we should be using.
You can observe 1 millimeter from the sea level.
Yeah. Sorry?
Will the wideband upgrade help?
Yes, in 10 years, yes, definitely.
The problem is resolution, I think. Yes. I mean, ALMA can observe 7 millimeter and 3 millimeter, but the resolution is very low. So I don't know if we can study compact disks. I mean, ALMA is very good to observe standard disks.
Okay.
But the question is not just about the resolution, but also sensitivity. And for some of the disks, if you do not give enough integration time, you will miss some substructures. So say like this lupus disk, if we give them more integration time, we might find more substructures. So just with the current capability of ALMA and give more time, like more years, then we may still find something new.
Yeah, I mean, in a sense, the community is used to shorter integrations. And we have to start pushing to longer integrations and since it's community review. But another point, for the interdisk structure, James Webb offers opportunities there from the chemistry. So Sierra, for example, showed a picture where if you're missing the inner AU, basically you remove all the hot water, all the hot gas that would form water. And so with Webb, I think we can find transition disks chemically. Now, maybe not, we won't be doing gaps, but we certainly can tell something about planet formation in the inner AU chemically. And there's another example. So CH3 plus was detected with Webb, and that's a very important ion for the carbon chemistry. And that was revealed, one in an irradiated disk, but also in the irradiated inner edge of a transition disk, DW Hydra, essentially. So again, chemically, we're going to do this, and we're getting these surveys. We're getting hundreds of disks. And let's also remember that, we're going to have 80 disks from the DECO program that will have C-to-O ratios, and for about 60 of those, maybe 50, we're going to get C-to-O ratios in the inner disk as well. So we're getting statistics, but it's taking time. I mean, it's been a decade, for crying out loud.
Sierra wants to.
Yeah, I just wanted to say something else about the compact disks, which was related to my question about the gas disk size versus the dust disk size. So it seems like, from Fang's answer to me, is that it seems like even these compact disks do not have this size ratio between the two that really indicates efficient radial drift. So we're talking about these compact disks, like probably they were just born small in that case. It's not necessarily that radial drift is then set in the outer disk size. So that's just an important thing when we're thinking about pebble transport. In these compact disks, that's not necessarily what is set in that outer disk size.
Mm-hmm. So I wanted to point out, our own solar system was a compact disk. There's an abrupt edge to the cold classical Kuiper belt at 47 AU, and that's the last place where solids were forming planets. When I reviewed this recently, I think that there is a lot of evidence for gas disks generally being twice as large as the solid disk. So I assume our solar system extended to 100 AU, but that is smaller than disk like HL Tau. There's a really strong correlation between disk size and FUV in the local star forming environment, which is one of many reasons I think our solar system was exposed to about 100, G0 of 100, and formed in a high mass star forming region with lots of implications for disk evolution.
Okay. So one of the things, incidentally, we want to do is encourage some of the, shall we call them, early stage, early careers people to class 1. All right, okay. There's no class 0 then, no? Okay. So any questions from that part of the audience? Yes? Yeah.
My legs, thank you.
Yeah, saving you work.
So this is really continuing. Oh, sure. Stephen Giacolone, Caltech. So this is, I guess, sort of continuing the previous conversation. And again, like Lauren, I'm sort of approaching this from an exoplanet observer perspective, so maybe not as familiar with a lot of the early disk stuff that folks do. But how much work has to go into just our understanding of really star formation to get a better picture of these models? Like you said, some of these disks might be born compact rather than having to get like that via radial drift. And so how much of this question is limited just by our basic understanding of star formation rather than the disk physics and chemistry itself?
Good point. There are issues in exploring disks at the very earliest phases, yes, when you are surrounded by or have a large core, as I understand it. There are, of course, some observations, but they're quite limited. So that would help address that question, wouldn't it? Yeah. Any other comments on that, Lee? Yeah.
I'm trying to remember John Tobin's e-disk protostars.
Yes.
It was something like, what, 50 maybe? 50 objects, 70 objects in John's, in his e-disk protostar? Okay. Okay.
So the e-disk, yeah, to look at the, I think, go ahead, Rob. I was going to say, for example, one of the things that I think people are appreciating that they don't really understand right now is the accretion history in the early phases onto the protostellar disk. So it was assumed previously that there was some sort of smooth, continuous, and then at some convenient time for us, it shut off and was zero after that, and so we could have our nice simple disk models. And now the people who do these very complicated three-dimensional simulations have ruined everything and said it could be episodic and occur. So I'll give it to Ralph first, and then. Okay. So there is that sort of elephant in the room.
So I think that's a great question, and there's whole parts of star formation conferences devoted to this, how disks are forming, because we can now see evidence of late accretion events, streamers from large scale, over thousands of AU that can rejuvenate a class 2 system into almost a class 0 disk. So all this kind of variability is a new space for thinking about disk formation, and I don't think anybody's really thought through yet what that would affect, how that affects our ideas of planet formation. A late dump of dust, on the system, who knows? So I do know for MHD theory, or let's say turbulent models, if you go back to, decades of simulations, that you see that in a turbulent environment, disks do not form by the collapse of a rotating thing, okay? That's classical stuff. That's what I learned when I was in graduate school. That era's gone. We do know that in a turbulent environment, there's streamers, disks formed by collisions of a number of filaments, exactly. They do result in a local angular momentum region, but the turbulence the local turbulence provides the local angular momentum, not some big cloud. So this is a highly transient event, perhaps continuously fed, and all of that matters. Most of the calculations that I and a lot of people do are with isolated disks, and what size you decide to pick for your disk determines everything, right? If you have a disk wind, that drives a vector flow inward, so the disk always becomes more compact. It will always be denser than in the viscous model where stuff goes outward. That is a very important difference in what you'll get for your planet formation. And I always thought that as compact disks is evidence that MHD wins, or breaking of some kind must be important in creating those systems. Why that didn't happen in the large disks like HL tau, clearly there's a stochastic process involved. But I think this is a very deep question, and it links the star formation and the planet formation conditions very profoundly.
Yeah. Can I add to that? Absolutely, it matters a lot what formation environment. If you have streamers, which we're seeing, or if you have a low angular momentum collapse, you can go into the inner disk and viscous spread out. And people debate this, but if you're in a region like Orion or more massive than that, you're photoevaporated like within 100,000 years after it forms, and you don't have opportunities for late additions. And I think that's a really important thing. And only a third of systems form in a Taurus or Iga region where we've seen these sorts of streamers.
Just a comment on Steve's comment that, so for example, if you look at the Orion Nebula, the region where the stars, where the disks get evaporated is actually encompasses a small fraction of the stellar population. So unless they're on really elongated orbits, you can't just look at the proplyds and say, okay, that's the majority of the stars, right? I got myself confused. Ted corrected me, but we now have about, so problem with early accretion is we can't see the protostars, right? But we now have about 30 protostars that have measured masses to some from Keplerian rotation of the disks. And so if you make an estimate, given the mass of the thing, what the stellar contribution would be outside of accretion, like two-thirds of the things that have been measured have almost no accretion luminosity. It's mostly stellar luminosity, or maybe 10 to the minus 7 solar masses per year, which would not make a star, in a protostellar lifetime. There's some bunch of guys that are accreting fast enough, or at least have high luminosities. So, with small statistics and obvious biases, you could make an argument that there's kind of a bimodal distribution of accretion rates amongst the protostars. And, if we could get more protostar masses, maybe we could really tell whether that's the case or whether it fills in. But it was surprising how many of the class 1 objects basically were consistent with pretty much just the star and not the accretion.
Would that be just the aspecticity?
Yeah.
It probably is. Yeah.
I'd like to make a remark about why we are talking so much about observations here at the Institute for Theoretical Physics. And I want to explain that with an equation I'm going to write on the board. And if that's too difficult to show that one, it's a simple enough equation I can go back there and write it. So I just need a piece of chalk.
Don't use the upper one. There's a notice. Do not use upper blackboard here.
The back, I can use that one?
No.
Oh, okay. So,
there.
People are talking about what the value of alpha is. Yeah, I think he'll accept this equation. So we have theory, yes, MHD, because we know we see that there's this activity and we want to get this and we can fit this with this ionization. But there are basic bounds we can put on alpha from straightforward theory. What we know is, let's see, maybe I could do it in the light area. And that is why we are spending so much time on observations. That is the molecular viscosity. It's a low number, because it varies at different spots in the disk. And so that's why even in the Institute for Theoretical Physics, we need a little bit of observations. Kolmogorov made some progress on turbulence in the 1940s. There have been some things done since then, but it's circumstantial. Anyway.
Yeah. Okay.
I just want to know if anybody's going to say 10 to the minus 19 is possible. Okay.
We'll just leave that there as a...
That's why it's greater than, less than approximately.
Okay.
Can I just briefly answer a question from Ralph about damage traps? I agree with you. This must be the most common ones, and I would say that they are all leaky because when I did my 2012 paper was assuming the sonar flows type of traps, which are very low amplitude, and they will lead a lot. They will make a lot of pebble flux to the inner disk. So I would expect that none of them are as strong as a giant planet trap, and giant planet traps are leaky anyway. So I would say all of the traps that all these disks have are leaky, and they have to be leaky, otherwise we could not explain the dust flux decreasing from class 0 to class 2, late class 2 disks. We see that we know this, that the dust mass decreases, and we cannot have that if we have very efficient trapping. Yeah.
Okay. Right, so just moving on a bit, because we're quarter of an hour until our reception by our hosts. Now, I think to some degree, Peter Abraham's questions here about infrared monitoring have already been to some degree discussed. We all feel a little bit of, shall we say, optical monitoring envy at the moment of what's coming in the future compared to the infrared. But I did like his comment about convincing the JWST panel to give more time for more than one epoch. So that's a reasonable point. Another question was to do with the inner rim, by Joseph Varga. Is it rounded, wall-like? What shape is it? And what's the origin, and which is something we haven't discussed too much, I think, of the emission within the inner rim? Is it from large grains, refractory dust, optically thick gas? What's actually there that we're seeing in some cases? We've talked about dust traps, etc., I think, at this point, and the composition of the dust in the inner few AU. Are there any comments that people want to say about emission and within the gap region as to what about the type of dust that would be present there? Obviously different. No? Oh, okay.
Well, one thing I noticed lately is, that there's been a decline in the number of radiative transfer papers on these topics. 15 years ago, that's what you would do to extract something from these visibility curves and things, right? You couldn't make an image. You would use there's a proliferation of radiative transfer codes and 3D models and things. But, now that we're seeing things as more complicated, it sort of like makes you wonder how we can extract the physical parameters people want, when you don't have like extremely good data, and you can actually try to do something very complicated. So so just a comment that as an observer, we would like to take these models. We have Matisse data, we have all these multi-wavelength data sets, and, we would have dreamed 15 years ago that we could put this in a model and extract a lot of great physical parameters, but now it seems a little bit hard to know what even to do with it except start talking about phenomenology and what's the basic picture. So just a comment.
Any other comments on that? No?
So John, what do you think the problem is? Is it non-axis symmetry? Is it even more complicated than that? Because there are Monte Carlo things that if you ran enough photons, maybe you could do something, right? But what could you be more specific about? What the complications are?
Well, I just mean, I think if we just fitted a single model to all these multi-wavelengths and tried to do some SED and everything, we would just get numbers out that weren't necessarily what they'd just be a best fit. They wouldn't actually reflect, if you have rings or if you have asymmetries and you just start fitting axisymmetric models with, power law, surface density profiles and all the things we love to do. I just don't know if it would be meaningful, what you get out of it. That's all. So it's just frustrating. We would like to say things, what's the flaring angle as a function of radius? What's the mean dust size, as a function of radius and height in the disk? These are all things we can do if you had a simple axisymmetric disk that you could fit. But when it's dominated by substructure and, strange temperature profiles and things, it's just, and again, I'm just trying to express a frustration that we had hoped we could extract a lot of great conditions that now I'm not sure we can do. Yeah.
Yeah, just to complement on that, also we've seen a certain number of simulations that are very expensive in terms of computation. So usually you explore a very small parameter space, whereas in the observations we have a great variety. And to me that's been a problem working with theorists, is that at some point you have to match data with simulations that are really limited in exploration. So we need to find some way of determining what are the essential physical parameters in order to better run the simulation adapted to the variety of what we have.
Yeah, and while I'm walking the microphone to Joseph, I think Takehiro's results really woke me up, because suggesting that just a 5%, for example, change in the alpha of the dead zone would have tremendous consequences for what we would expect from the mass inside.
Yeah, this is just comment and John's comment. So about the complexity of the disk structure, this is now an issue because we have a sparse baseline sampling, and this causes that for many disks we see that these have substructures and asymmetric substructures, and we just with this data we cannot know where to put that exact asymmetry. So, but we also have a bunch of simpler objects which do not show those strong closure phase signal. And then in that case we can be sure that there is a circular or elliptical symmetry. So maybe that's also a path to take those objects.
Okay, thank you. Stefan?
Well, I think in some individual cases we also deal with some emissions that is difficult to simulate with traditional radiative transfer, like these quantum heated particles or these highly refractory dust grains where the laboratory data might be missing. So I think that also from theory that is something to catch up so that we could really model what we are seeing. And so this communication is maybe not happening yet between morphology-focused observers and theorists that really go down to the microphysics level.
Okay, so anyway, we're nearly past. This is my last slide, and it was a questions from Sierra Grant. I think to some degree we've already talked about the first two, right? But talking about going down the mass ladder, what happens at even lower masses, and what does this mean for planet formation? Is there some further thoughts on that? Yep.
So this is more of a comment/question. So we know that radial drift is very dependent on the size of the pebbles. And we have ALM, which is fantastic because we can now see things that are millimeter size and I don't know, maybe even centimeter. And I'm more curious about bigger size objects because these are the things that we do not see and we don't know what mass they represent. Or maybe we do, I don't know. So
I don't know if there are any thoughts about that, and I think that is important because in the core accretion model, we want to follow the dust from the micron size up until to the planetary embryo and the planets eventually. So I'm wondering if there are any ways we can give constraints on rings of planetesimals, because these are not something that we will see in the nearby future.
Very good question. Sorry.
I want to add to that question. I'm hearing a lot today here about dust disk being, some disk being smaller than traditionally thought, and also the traps being a bit leaky. And from reading traditional pebble drift theory about meteor-sized boulders being pretty fast, that they can reach the inner edge quite quickly. So I'm worried about, I mean, in my mind, I would just assume, oh, well, they were trapped at the dead zone and that's it. But how is this problem now being addressed in a way? Is planet similar that, but I'm specifically worried about meteor-sized boulders.
Yep.
Sorry.
Well, so the reason why the meteor-sized boulders drift inward, that's because they would follow the pressure gradient, right? But then if there is a trap, then they would be more efficiently trapped in that case. That would be my guess.
They also don't exist.
I mean, so the NGVLA offers the best opportunity to explore what happens close to the meter-sized barrier. So that's just an observational statement. There is some work out there that Joe Najita, for example, claimed that the ratio of, I guess it was CO2, or was it C2H2 to water, no, it's HCN to water, was telling you that when it was high, that planetesimals were present, because basically cometesimals were present, trapping the water and letting carbon be in the gas. And in TW Hydra, Melissa McClure has a paper on similar to what Marbley was talking about, in a way of looking at accretion streams and hot gas closest are, and finding that carbon was completely depleted. And again, she claimed chemically that planetesimals were present. But all of these things are, it's a ladder of assumptions based upon the chemical content. So it's very, very hard to tell that planetesimals are there, except we know from the solar system that it tells us that they are.
Okay, I think on that positive note, it's just at least we've come to a semi-definite conclusion that alpha is probably greater than 10 to the minus 18. That's very positive. Okay, well, thank you for a really interesting discussion. And can I ask you please to thank all of our speakers. Okay, it's time for more discussion over reception.
And let's thank Tom for a very stimulating discussion today.